we have a 3 by 3 matrix. We want to solve x prime equal to a times x. In this case, it will be a defective eigenvalues case. In this case, A is a upper triangular matrix, and therefore we can see immediately the eigenvalues. Eigenvalues are entry on the main diagonal. Lambda 1 equal to 1 and lambda 2 equal to 3. So lambda 1 has multiplicity 2, the other one multiplicity 1. Let me do the multiplicity 1 first. Let's do that computation so we get one eigenfunction for sure first, and then deal with the other case later. Lambda 1 equal 3. Now we need to find v. Minus 3, minus 3, minus 3. So what we are doing is a minus lambda 1I times v1 equal to 0. We are trying to solve for v1. So this one is a matrix minus 2, 1, 0, 0, minus 2, 0, 0, 0, 0. So we have, think of that as times A, B, C. This one will give us minus 2A plus B equal to 0, minus 2B, 0, and 0 equal to 0. So we have B must be 0. And A is also 0. Because B is 0, then A is 0. C can be anything. C is free. The vectors of the form A, B, C now will be 0, 0, C. So 0, 0, 1. Eigenvectors V1 is 0, 0, 1. Okay, so we have done with the easiest case where multiplicity is 1. Now we look at the other one, lambda 2 equal to 1. Matrix A minus lambda I zero, 1, 0, 0, 0, 0, 0, 0, 2. Again, you solve this for A, B, C times this matrix times A, B, C equals 0. We have B equals 0 from the first equation. Second equation, 0 equals 0. The last one, 2C equal to 0. 2C equal to 0. A, B, C now of the form A is 3, B, C are 0. So A, 1, 0, 0. We have 1 eigenvectors. V2 is 1, 0, 0. So it's defective. You see that lambda 2 equal to 1 is defective. We miss 1 eigenvectors. And we find the generalized eigenvectors. Now, there are two ways we can find the generalized eigenvectors. Let me call this V2. Oh, sorry, V2, we have this already. Let's call it V3. So, by definition, because this is defective one, it's missed one eigenvectors. So, that eigenvectors V3 is actually the solution of A minus lambda 2I square equal to 0. If You remember the case of A is 2 by 2 matrix. When we miss one eigenvectors, when raised to power 2 is will give us a 0 matrix. It's not the case now when we have 3 by 3 matrix, but we miss only one eigenvectors. So this matrix square is non-zero. So one way you can do that is solve this. That method 1. Solve for V3. And make sure that V3 is independent from the actual eigenvectors. We have two eigenvectors. We already have two actual ones, V1 and V2. V2 is this one, V1 is this one. Make sure it's different from that. And then you need to build the chain again, because we have V3, we need to update V2 by V2 equal to A minus lambda 2I times V3. So update that by plug in V3, you found it, put it here, then you get V2. That is the first method. The second method, you can compute V3 directly from this equation. So here we only know V2. So let's say find V3 method 1. Here we find V3 method 2. We use the relation here is V2 equal to A minus lambda I times V3. Use this relation. V2 we found that V2 is 100. Now let's do both methods and see. Method 1, 5V2 like that. You need to raise the power A minus lambda 2I squared. A minus lambda 2I. Here's A minus lambda 2I. You need to square it. So 0, 0, 0, 0, 0, 0, 0, 0, 4. So now I need to find V3. So that is matrix times V3 is 0. So think of that as a B, C. That gives us 0 equals 0, 0 equal to 0, 4C equals 0. So C equal to 0. And AB is free. So with any vectors AB 0. So that is that one. But that one needs to be independent from the actual eigenvectors. So now the vectors of this form and independent from the actual one, from V3 100, from V2, sorry, independent from V2 100, from V2 100. So we choose V3 0, 1, 0. So this is our generalized eigenvectors associated to V2, lambda 2 equal to 1, right? Equal to 1. So now you need to update V2. V2 is given by the formula A minus lambda 2i times v3. A minus lambda 2i times v3. A minus lambda to this matrix times 0, 1, 0, 0, 0. So it is the same as the one we had. Perfect. So that is the first method for finding v3. The second method, you just solve this one. v3 in our space of this matrix. A minus lambda 2, A minus lambda 2i it is. So we need to find v3 at cost non-zero, such that this one times v3 equal to v2. v2 is vectors 1, 0, 0. So this one gives us v3 is ABC. ABC, then you have B equal to 1, 0 equal to 0, 2C equal to 0. So C equal to 0, B is 1, A is 3. So we have ABC of the form A, B, C equal to A, 1, 0. So we can choose as to be V3 to be 0, 1, 0. That will be good. Any A you like. So this is our V3. This is our V2. This V3 is generalized one. Same, we obtain the same thing for the first method. So it seems to me that method 2 is easier in this case. Now we form a solution. The first one is the actual eigenfunction. It comes from lambda 1 and v1. Lambda 1 is 3. Lambda 1 is 3. This one. V2 is this one. Lambda 2 equal to 1. And V3 1, 0, 0, 1, 0. Generalized eigenvectors. And these two are the actual eigenvectors. So the first one, V1, will give us V1 lambda 1 will give us, let me call x1, x1t. V1 e lambda 1t. Second one's called x2, V2 e lambda 2t. The last one, x3, of course t. V2t plus V3 e lambda 2t. So let's write them all here. Plug in all the values. You have x1 is 0, 0, 1 e 3t. x2 V2 1, 0, 0 e lambda is 1, so e to the t. x3 v1 v2t plus v3 v2 1 0 0 t, so times t times t times t, still t 0 0 plus v3 is 0 1 0 0 1 0. This vectors e t should be cleared up. So this actually v2 t v3 e lambda 2t. Remember this. So you just plug in v2 t plus v3 plus y. You get this. Same here. v2 e lambda 2t. So general solution: xt c1 x1 c2 x2 c3 x3. Yeah, you just replace this one for x1, this one for x2, this one for x3, c1 c2 c3 as real numbers. We get general solution. That's how we do it for this case.